1 inches to the power 4. Let me do it again. 1.792 times 0.5 times 6 power 3 divided by 12 plus 5.376 times by 3.475 minus 3 squared, 7.341. And then finally, oh, ran out of space. It's okay. I'll do over this side. I'm going to calculate IZZ4. Okay, so this is 1.792 multiplied by 12, multiplied by 0.5, about 3, divided by 12, plus by 10.752, multiplied by 6. No, 3.475 multiplied by 6 here, right? 3.475 minus by 5.75, and the whole thing squared. Okay, so 1.792 times 12 times 0.5 power 3 divided by 12 plus by 10.752 multiplied by 3.475 minus 5.75 close bracket squared, 55.872. Okay, so 55.872 inches to the power 4. Let me do it again. 3.475 minus 5.75 squared times by 10.752 plus by 1.792 times 12 times 0.5 power 3 divided by 12. 55.872. So therefore, I total is equal to 62.529 plus by twice of 17.341 and plus by 55.872. Okay, so 62.529 plus by 2 times 17.341 plus by 55.872. I get 153.083. So 153.083 inches to the power 4. Okay, let me do it again. 62.529 plus by 529 plus by 17.341 times 2 plus by 55.872. 153.083. Okay, right. So now we have everything now. Okay, so let me I'll give you some time to copy. I know some of you are copying it. Okay, so now we are going to, I'm going to take this entire image, I'm going to copy the whole thing. And we're going to move over the other side, our next page. Okay. So our centroid is 3.475 from the top. Right? So our centroid is 3.475. Okay, so if I'm going to sketch roughly where our centroid is, our centroid is roughly about here. No, wait. Okay, so 1, 2, 3, 3.475, 3.475. So our centroid is somewhere around here. Our geometric centroid. So this is our centroid. Okay, and then we've seen that our moment vector is acting this way, right? So we know on above the centroid is compression, below is tensile. Exactly the same thing like what we've learned. Okay, nothing changed. The rules still apply. Okay, so from here we know, right? So this is where the analysis come in. Okay, so the question asks us to calculate the maximum. To calculate determine the maximum stress in the, so it only say the maximum stress. It did not say the maximum tensile or the maximum compression. Okay, so let's focus on aluminum first. Okay, so let's look at aluminum. And we know that the aluminum is under what? Compression loading. Okay, so aluminum is under compression. Compressive is up to you. Loading only. Right? It will not see any side of the tensile bit because the tensile has to be below the centroid. So it's all under the compression mode. Okay. So from here we can write this and the maximum will occur at point that I'm circling it now. I call point alpha. Right? Because it's the furthest distance away from the centroid. So alpha or y alpha, point alpha, and y point alpha is equal to, we know the length is 3.475. Okay. So as we declare now here, aluminum is under compression. So stress in the x direction of aluminum is equal to, so you have to put in the formula, you have to put in the coefficient. Okay, so 1. So let me write out the formula first. Okay, so it's N aluminum, right? And then M Z over IZZ multiplied by Y. Okay. So this will be equal to 1. M, the moment we calculated, is equal to, what was it? I can't remember now. It's equal to 10800. Okay, 10800. Y is 3.475. And divide by the I is at 153.083. And it's under compression minus. So this we will get 10800 3.475 divided by 153.083. So this is equal to 245 minus 245.161 minus 245.161 psi.
Sir, can you quickly go over how we get that 3.475 for Y?
So the distance from here to here is 3.475.
Oh, okay, thank you.
Okay, does that make sense?
Yes,
right?
sir. Thank you.
Yeah, so that's where the 3.475 comes in. Okay. So now the next question is determine as I said, the question only asks determine the maximum stresses. Okay. So next we are going to calculate Kepler. So Kepler is under both compression and tensile or tension loading, right? So why is that? Because part of the Kepler is above the centroid, part of it is below the centroid. So I'll call this point I, and this point over here, point J. So point I has a maximum compression. Point J has a maximum tensile. So the maximum compression distance is furthest away. Okay, so over here, from here to here, we know that the distance we calculated out earlier, it was at 2.525. Right, 2.525. So we know the compression will be highest. Okay, for this stage, we know the compression. So we calculate the maximum, or we declare the highest stress or maximum. Okay, we use the same word as the maximum stress for Kepler is in compression. Okay, so we know that y at point I is equal to 3.475 inches. Okay, so we are going to find the stress X of Kepler. So now we have to put in the coefficient, which is 1.792, multiplied by the moment, and it's in compression minus, okay, 10800, 3.475, and we divide by the second moment of area, 153.083. So this will come out to be, so 1.792 times 10/100 times by 3.475 divided by 153.083 is equal to minus 439.329. Okay, so minus 439.329 psi. Now I realize that some of you do too much rounding, okay, in your term test or your quiz. Make it 3 decimal points, okay. 3 decimal points will be fantastic. Or not, you do too much rounding, and sometimes the rounding will cost you marks, unfortunately. Okay. So if you're interested in tensile, okay, so let's say we're going to calculate maximum tensile stress in Kepler. Is straightforward, yes or no? So I'm going to do over here. So maximum stress or maximum tensile stress, just to show it to you that it's lower than compression. So again, Y now is at J. This is 2.525 inches. Okay, so stress X Kepler in terms of tensile. So it's again 1.792 multiplied by the moment, the point of interest, divided by the second moment of area. So this is equal to 1.792 times by 10, 8 times by 2.525 divided by 153.083. So it's 319 positive 319.224 psi. Okay. So you see that sandwich material is not that difficult at all, right? Okay. The tricky part, okay, not the tricky part, but you have to include your N coefficient down here, okay, reference material coefficient, and you have to just pick your reference material for this. We pick aluminum, and you just do your calculation, okay. So everything still the same in our analysis, okay. I'm going to touch on briefly, okay, on composite material under axial loading, okay, because in the next section we're going to look at eccentric symmetrical loading, okay. So in eccentric, so we've been doing centric so far, okay. Eccentric, there's an axial load, okay. So I'm going to introduce to you, since we're in composite material, how will composite material behave, right? Is it as simple as bending, right? Is it as simple as bending? So this is due to bending, right? We can see down here that this is due to bending, right? So bending is straightforward. You just put a coefficient in front and you run with it. Now for axial loading, it is not the same, okay? Is it more difficult? No, it's not more difficult. The formula, you just have to derive a set of formula, okay? So let me briefly, okay, describe or derive for you the formula for composite material under axial loading, okay? So we are going to look into composite material.